Bismillahirrahmanirrahim. Good morning, jury members, ladies and gentlemen. Thank you for being here today, and also thank you for accepting this work for oral presentation. My name is Abdelatif Gadoum, a lecturer at the University of Ouargla. I'm here today with a great honor for me to present our research entitled by Comparison of Methane Dissociation in an Inductively Coupled Plasma Reactor for two input powers, Pin equal to 100 watt and 500 watt. According to the World Health Organization, air pollution kills an estimated 7 million people worldwide every year. The data shows that 9 out of 10 people breathe air containing high levels of pollutants. 23% of all estimated global deaths are linked to the environment. 3.8 million deaths every year as a result of exposure to indoor smoke from cooking fuels. 4.2 million deaths every year as a result of exposure to the fine particulate matter. Methane molecule is the simplest polyatomic hydrocarbon, and it is present in the atmosphere of the most planets and on the interstellar surface. It is also used in plasma in many fields of technology and is considered to be a gas or to be a good test gas. Methane is also a potent greenhouse gas, which is roughly 30 times more harmful to the climate than carbon dioxide. The main objective of this study is to do modeling of inductively coupled plasma in methane at low pressure. In the present model, we include the motion and the collision of both neutral and charged particles by considering 19 species and more than 40 reactions. The results show that the dissociation rate of the methane is about 13% for input power Pin equal to 100 watts, while 75% for Pin equal to 500 watts. We will show also that the dissociation reach more than 90% for 700 watts. Plasma is a mixture of ions, electrons, and neutrons. They are generated by injecting sufficient energy into a gas so that it becomes partly or fully ionized. The energy can be supplied in the form of electrical fields, chemical reactions, or heat. This energy is stored in different degrees of freedom of plasma, such as in the form of kinetic energy of internal excitation of plasma species. The methane molecule is the simplest polyatomic hydrocarbon, and it is present in the atmosphere of the most planets and on the interstellar surface. It is also used in plasma in many fields of technology and is considered to be a gas test. Several studies have been taken place that were interested experimentally and numerically in pure methane, or by mixing it with other gases such as hydrogen and nitrogen. The electronic impact collision reaction used in this numerical study are all shown in our paper entitled the set of the electron collision cross section for methane molecule for more informations. The electronic impact collision reaction are also shown here in this table. The reactor used for the modeling is shown here in these figures. The coil are as shown here on the top of the reactor. A simple ICP reactor is a cylindrical chamber of radius R and height H in which the gases are injected. The sources are maintained at low pressure between 5 and 50 milliliter by external alternating electric fields. The frequency range is typically between 1 and 100 megahertz. In an inductively coupled plasma, the radio frequency currents in the coil generate an RF magnetic flux which penetrates in the plasma region. The time varying magnetic flux density induces a cylindroidal RF electrical field which accelerates the free electrons and sustain the discharge. The description of the reactor used in this modeling work is shown in this figure. This reactor is called ICP GEC, the gaseous electronic conference. The mesh performed in this study is shown here in this figure. The model of inductively coupled discharge that will be detailed in the following operates in an autonomous way, whose fluid model of species is associated with the electromagnetic equations to calculate the electric field caused by a temporal variation of the magnetic induction of the coil. In this model, we will include the gas flow from the inlet to the outlet using the Navier-Stokes equation. In this figure, we show the spatial distribution of the gas velocity in the reactor. This speed is obtained by the resolution of the Navier-Stokes equation. It clearly shows that the velocity is very important in the inlet of the reactor than the other sides. Its value at the reactor outlet is almost half of the at the inlet due to the large outlet section in the comparison of the inlet. In this second figure, we show the spatial variation of the magnetic potential vector created by the coil. The electric field induced by the temporal variation of the potential is the source of energy that will be recovered by the electrons to maintain the electric discharge. The main results are shown here in this figure, which is the variation of methane density in function of power. Here we preferred to show not just for the results for 100 and 500, but from 100 to 7 or 800 watt. As we can see here for the 100, the rate dissociation is very weak, and this is because of as shown here in the figure, the right side, the top, because of the power is very weak, then the reactor is behave like the capacitively coupled reactor. In this case, the magnetic field is very weak, then the electric field dominates in the reactor. This causes the electric field push the charged particle toward the walls, and then the dissociation rate is very weak. But by increasing the power, the electrons and charged particles are confined just under the coils, as shown in the figure, the right side down. The electrons and charged particle are confined, then the dissociation rate is very high, and this can be resumed in the figure at the left side, where we can see the two mode or the three mode of operating for the inductively coupled plasma reactor. The first operates in the E regime, where the electric field dominates and the magnetic field is very weak. For the second is the transition between two regimes. The third regime is the H regime, where the reactor operates with a strong magnetic field. In this case, the charged particles are confined under the coils, and this causes a high dissociation of the gas. As we can see here, for increasing powers, the dissociation of methane reach more than 90% for 800 watt. In this work, this work is part of the general context of radiofrequency plasma encountered in many research fields such as micro and nanoelectronics industry, for the deposition of thin films for etching patterns on silicon substrates, as well as on nuanced materials or for photonics. The purpose of this study was to gain a better understanding of the discharge and plasma, as well as hydrogen production. The main objective of this work is to develop a numerical model that allows to show the possibility to use the inductively coupled plasma reactor for dissociation of methane, also for other gases. The dissociation of hydrocarbons by cold plasma is strongly required as an environmental technology, for example for hydrogen production. It is known that the hydrocarbons can decompose directly into carbon in the solid state and hydrogen to fuel cells for the production of electricity. The non-equilibrium cold plasma that are characterized by high electronic temperature in cold gaseous environment can be generated by electrical or electromagnetic sources, such as cold plasmas from radiofrequency discharges, microwave plasma, dielectric barrier discharges, and also corona discharges, etc. As a resume, we can say that for this study that we obtained two objectives. The first is the dissociation of methane, which is considered more harmful than carbon dioxide by 30 times. The second objective, when we perform this dissociation, we can also obtain the hydrogen gas, which can be used as a fuel. In this study, we don't show the results, but we obtained more than 30% of product as hydrogen molecules. And finally, thank you for your attention.